Hello students, welcome to All Force e-learning channel. This is K. Nageshwar Rao, physics faculty, and today I am going to discuss with you one topic from electrical capacitance. Electrical capacitance related topics were almost all covered so far, starting from the fundamental data and then combination of capacitors, energy stored in capacitor, common potential, all these topics and their applications were completed. And there is one last final topic, Van de Graaff generator. Van de Graaff generator. Let us see what this Van de Graaff generator is. See, the name has, a few things. Sometimes names, they don't convey any conceptual information. Van de Graaff is a scientist's name. Okay, it's a generator. What it generates, we'll see. Eventually, we'll come to know everything. Okay, I'm going to explain to you based on what principle this Van de Graaff generator works, how it can be constructed, how the entire working procedure occurs inside the Van de Graaff generator, and I'm going to explain the uses also. Okay, so I'll start with the uses so that you will come to know what actually this Van de Graaff generator does. Little interest can be built up like that. So, Van de Graaff generator, basically it's a particle accelerator. What it does? It accelerates charged particles. Let us ask ourselves, why is it necessary to accelerate charged particles? How it can be done? See, to set any body into accelerated motion, you can use several means, in several ways you can do that. But when you are dealing with a minute charged particle, you cannot do just like that, like you cannot give a push mechanically. You need to employ different other techniques. The best one is when you wanted to accelerate a charged particle, you can supply some potential difference, and using that potential difference, it can be set into accelerated motion. For example, if you take in a region, let us say a charge Q is there. If you wanted to set this charge Q into accelerated motion, what you can do? You can create a potential difference. You can take a positively charged plate here, and you can take a negatively charged source there, and there is a potential difference. This is at high potential, this is at low potential, and what happens? This positively charged particle undergoes a accelerated motion towards right side. Isn't it? More the potential difference, more the acceleration it can undergo. This is very fundamental, which was already taught to you in electrostatics. Okay, so this is what I'm going to do now. I'm going to set this, set one charged particle into accelerated motion using Van de Graaff generator. Okay, now let us ask ourselves one more question. Why is it required? Why is it required to set a charged particle into accelerated motion? For example, think about bombarding a nucleus. Atom, a heavy atom is taken. Inside the atom, deep inside the atom, what will be there? The core of the atom, nucleus. It's a positive, right? High positive charge will be there inside the nucleus. Now, my interest is, I'll take a plus Q charge. For example, let us say this is a nucleus. It has a lot of positive charge, and this is the boundary of this atom. Okay, here within this space, all electrons are revolving around this nucleus. Let us assume like that. I have taken one plus Q charge, and my interest is I wanted to project this plus Q charge, straight ahead towards this nucleus. I wanted to bombard this one. What happens? Obviously, when this plus Q approaches this nucleus, since this is positive, both repel each other, and the repulsive force builds up significantly when this plus Q charge approaches this nucleus. Why? According to Coulomb's law of electrostatics, force of repulsion is inversely proportional to square of the distance of separation between the two charges, isn't it? When this plus Q is reaching this nucleus, what happens to the distance of separation between these two? Distance of separation decreases. When distance of separation decreases, repulsive force increases abnormally, and probably this plus Q may not be able to come in contact with this one physically. It gets scattered like this or like this. It may undergo scattering, isn't it? But if my intention is, I want this plus Q charge to make physical contact with this one, to bombard this nucleus, to break this nucleus into pieces. What I have to do? I have to accelerate this plus Q charge to such a huge values of velocities, to such a huge value of kinetic energy, such that even the repulsive force offered by this nucleus can be overcome. What happens if charge is, if velocity is more? It can enter, it can come in physical contact with the nucleus. Even whatever repulsive force the nucleus is exerting on the charged particle, it cannot do anything. Okay, so that is the purpose of accelerating charges. That is the purpose of investigating such kind of instruments. Okay, so using this Van de Graaff generator, I can give required kinetic energy, required velocity such that this plus q can make a physical contact with the nucleus and it can bombard the nucleus. So I hope you understood what this Van de Graaff generator does. So it builds up a high potential difference, and using that high potential difference you can accelerate charges, and those accelerated charges can be used to hit a nucleus or to hit any target. Okay, so basically Van de Graaff generator is particle accelerator. Okay, that's how you can remember. Okay, so let us discuss about principle. Based on what principle it actually works. Okay, see, when the principle thing comes into picture, we can talk about two points here. One is electrostatic induction. Electrostatic induction. The other one is, this is a little strange, so most of you may not be familiar with this one. I'll explain anyways. Action of sharp edges, or it is also studied under this heading corona discharge. Corona discharge. Electrostatic induction in the sense what? For example, if you take a heavily positively charged body, something like this, if it is brought close to a neutral body, this is neutral, then what happens? Charge will be induced. Whatever electrons are present inside the body, they will be attracted towards this surface, and on the other surface the positive charge gets accumulated. So that's how you can make sure that induced charge appears on the surface when a heavy positive charge is brought close to this one, isn't it? So that's what we call it as electrostatic induction. And I'm going to use this phenomenon while making sure that Van de Graaff generator works properly. Okay, somewhere I'm going to use this phenomenon. I'll tell you when the working is discussed. I'll tell you where this electrostatic induction concept is used in Van de Graaff generator. Okay, so let us talk about this action of sharp edges. So let us see what this action of sharp edges means. For example, if you take a sphere, let us assume that some charge plus q is given to this one. How much charge is present on this sphere? Plus q. Conducting sphere or spherical shell, whatever it is. When you give charge to a conducting sphere, solid sphere, or spherical shell, the entire charge appears on the surface. I hope all of you know the reason why it happens like that. Inside a conductor, the charge can move freely from one place to the other place if such a kind of flexibility is there. And all these things are positive entities. They repel each other. They were able to move. If they were able to move, what they will do? They don't attract each other. Here you have taken positive charge, so they repel each other and they push themselves such that they reach the surface of the sphere. That's where maximum they can go. Beyond that, they cannot go. They cannot jump from the surface, isn't it? So they get distributed uniformly like this in case of a solid sphere. And let us assume the radius of this small solid sphere as r, or conducting sphere as r. Okay. So if I wanted to talk about surface charge density, how it can be written here. Surface charge density is usually expressed with sigma. Sigma is equal to total charge by 4 pi r square, isn't it? What about potential of this one? Potential of this one is expressed as V is equal to potential on the surface or inside the surface is how much? 1 by 4 pi epsilon naught q by r, isn't it? So now I'm going to replace this q with sigma 4 pi r square. I can do that, right? So V is equal to 1 by 4 pi epsilon naught. What I can replace q with? Sigma into 4 pi r square. Sigma into 4 pi r square into by r. I'll tell you why I'm going with this mathematical treatment. I will tell you. Okay, there is a reason. Eventually we can connect this one with action of sharp edges. Okay, how does this action of sharp edges is connected with this one? Just wait and see. Okay, we'll try to understand. So here 4 pi gets cancelled and the r gets cancelled, and finally what you are left with? You are left with potential V into epsilon naught is equal to sigma r, isn't it? And here this sigma can be expressed as V epsilon naught into epsilon naught divided by r. Look at this equation. So whenever we get equations, what do we do in physics? We analyze that equation. We try to extract information. This equation, it is trying to speak something to us. Let us try to understand what it is trying to speak to us. Whatever this potential is there, potential is same everywhere on the surface, isn't it? So this V is constant, and epsilon naught, this is also constant. So what you can write here, you can write from this relation, what you can write, you can write like this: sigma is inversely proportional to r. Let us understand how this sigma is inversely proportional to r is connected with this one. What if you take an irregular surface instead of taking a conducting solid sphere? I am going with an irregular surface, something like this. Something like this. Okay, irregular surface. This is a conducting material. For this conducting material, if some charge is given, what happens again? The same thing. It moves. All the charges, they push themselves such that they reach the surface. They reach the surface. So let us say those charges got distributed on the surface, but here charge distribution won't be uniform. Why? See, for example, if I take one point somewhere here, from this point to this point, if there should be any charge movement, what is the fundamental requirement? There should be potential difference. Potential difference is something that drives charge from one position to another position. So if, finally if all these charges gets distributed and they were in their positions, further there is no any movement. What does it mean? Potential at all points is same. If at all, if any potential difference is there between this point and this point, there might be a movement, isn't it? And now there is no any movement. All the charge got, it's segregated on the surface, isn't it? So potential here and here at all points on the surface, like in the case of a regular shaped solid conducting sphere, here also potential is same on the surface, isn't it? Now look at various parts of this surface. If you observe this one, this is curved, right? And if wherever we see curved surfaces, we try to imagine a sphere out of that curved surface, or if you are having a curve, we imagine a circle out of that. Usually we do with many physics related phenomena, right? Here also I am assuming one such kind of circle or sphere, whatever it is. So sphere, I have taken a sphere. Okay, let us say this is a three-dimensional object. So this will have a certain radius of curvature, right? So I will take it as I will take this radius of curvature as R1, and here also you can assume one such kind of sphere, and these two will have a radius of curvature, and I will take that as R2. Obviously R2 is less than R1. If radius is less than, if radius is smaller, it is inversely related to what? Surface charge density. If R is small, surface charge density is going to be very large, isn't it? It means here charge density will be extremely high when compared to this place. This is having more radius of curvature. If R is more, surface charge density will be small. Surface charge density is small in the sense what? Whatever charges are there, they are distributed on a wide surface. And here, whatever large amount of charge is distributed on small area. It means the density of charge is very high in these kind of places. Okay. So if you take a sharp edge, what happens? When you go with a sharp edge, let me wipe it. So what we came to know? We came to know that surface charge density is inversely proportional to radius of curvature of the surface, isn't it? So if I take a sharp edge, something like this, okay. Something like this, sharp edges were taken. If I give some charge to this one, where the density of the charge will be more, here, density of charge will be more here. Here density will be more. If density of charge is more, what happens? Electric field intensity will be very high in the neighborhood of these sharp edges. When electric field intensity is very high, what happens? Whatever ions are present in the vicinity, if at all, if I keep a surface somewhere here, let us say there is a surface, neutral surface, what happens? Because of this high amount of positive charge, electrons will be induced on this surface. If the intensity of electric field is very high, what happens? Whatever electrons are present on this surface, even they can be pulled out. So there are several ways of extracting electrons from the surfaces. You can use radiation, that's what we call it as photoelectric effect. You can use electric field, high intense electric field. Even you can use heat energy, you can heat it. Thermionic emission, we call it as. Here what I'm doing, I'm using a high intense electric field. That is what it is doing. It is removing electrons from the surface. Such a kind of high intense electric field you can produce using these sharp edges. So that's how action of sharp edges is going to play a crucial role in what a Van de Graaff generator working. And whatever this corona discharge is there, here whatever these electrons are traveling from this object to these sharp edges, so such a kind of transfer of charge is nothing but corona discharge. That's what we see during lightning. Okay, so this is about the principle. Okay, hello students. Now let us talk about the construction. This is how a Van de Graaff generator looks like. What did I take? Let me explain the structure here. Whatever these are shaded, pillars kind of arrangement is there. They are insulating pillars. They don't conduct. Okay, and here I have taken a hollow metallic sphere, and inside of this hollow metallic sphere, one pulley is there. This is pulley P1, and this is pulley P2, and these two pulleys are connected with a belt which is made up of nylon. There is the reason for taking nylon belt. It's an insulating belt. Okay, and I have taken two combs here. This is C1, this is C2. These combs were having sharp edges. See, just now we have discussed about action of sharp edges, right? Okay, so here those sharp edges were taken. Okay, and this is a high tension source. Okay, and I'll tell you about this one later. Okay, one small chamber kind of arrangement is there. I'm going to put something there, and it will be allowed to travel along this pipe, and finally this is where it is going to meet with. Okay, I'll explain that later. So let us try to understand this. What is happening here? A high tension source is taken. Several batteries were arranged, and this is connected to a comb C2. Okay, and this comb is having sharp edges. Since this is connected, this comb C2 is connected to a positive terminal of the battery. A heavy positive charge accumulation takes place on these sharp edges. What happens when heavy positive charge gets accumulated on the sharp edges? Just now we have seen, right? The concentration of positive charge will be very high on these sharp edges. If that is the situation, electric field intensity in this region will be very high, isn't it? For example, if you are taking a neutral surface very close to this one, what happens? Whatever electrons are present on this surface, on this insulating medium, those electrons can be pulled with the help of this electric field intensity. That's what we have discussed about earlier, isn't it? Now, what is going to happen here? Here, these sharp edges having a huge amount of electric field intensity in its vicinity, it pulls electrons. Let me erase these positive charges. I will explain this. Right. So here, heavy amount of positive charge is given to these sharp edges, and that creates a high intense electric field intensity. That electric field intensity pulls electrons from this belt, nylon belt. So when the electrons are pulled, those electrons will travel along this direction, and here positive charge gets accumulated on the nylon belt, because electrons were removed. No, so this particular part of the nylon belt gets positively charged, and that positive charge doesn't travel anywhere because it's an insulating belt, isn't it? If it is a conductor, that charge goes all around, but this is insulating material, nylon belt. So whatever charge is created, that stays there only. Since you can move these two pulleys, you can rotate these two pulleys. What happens? This conveyor belt can move like this, right? If this pulley is rotating like this, what happens? This part of the belt goes up, and later what happens? The next part gets charged. So like that, positive charge continuously travels to the top, up to here. Okay, because the belt is rotating. So whenever the charge is created, that part goes up because pulleys are rotating, and next part gets charged. How it is getting charged? Electrons are removed because of this action of sharp edges, isn't it? So like that, positively charged part of the belt goes up. By the time it reaches here, what happens? Again, these sharp edges here, what happens? Because of this positive charge, electrons will be induced here, and here on the back side of this comb C1, positive charge will be induced. Okay, and these electrons will combine with this positive charge, and this part of the belt becomes neutral. Which part? This part of the belt becomes neutral, and this part goes up, and neutral part of the belt again, it travels down, and again it gets charged, it goes up, it delivers positive charge here, and like that, continuously this process, this cycle occurs. It repeats, and whatever positive charge is present here on the back side of the comb, it travels, it travels to this metallic sphere, and it gets accumulated on the top of the surface. Because whatever charge you give to any metallic surface, any shell, okay, where it will go? Eventually, it goes to the top of the surface. So like that, as long as this this entire process is occurring, the accumulation of charge increases on the metallic sphere. So at some point of time, there will be a huge amount of charge accumulated on the metallic sphere. So what do we do with that? See, children, when you have a sphere something like this, let us say some charge is present on this one, and because of that, let us say it has a potential V. It has a potential V on the surface or inside anywhere, the potential is V. Let us say I have placed a small charge Q inside of this spherical shell. Now what happens when a small charge Q is placed inside this spherical shell? It will have some potential energy. How you can write expression for that potential energy? U is equal to V into Q, potential into charge. So this is how it can be written. Now this is having some potential energy, whatever charge is present inside of this sphere, isn't it? Similarly here, let us come back to this one. Whatever hollow metallic sphere I have taken, now this is at a very high potential. This is at a very high potential. I have placed a particle inside this chamber, okay, whose charge is equal to small q. Whose charge is equal to small q. Okay. So now, because of this high potential, this one will have a potential energy, and that energy is equal to how much? VQ. Okay, and the potential of this charge is also how much? If at all, if that particle is having some significant size, it will have its own potential, and already this metallic sphere is providing some potential at this point. So both the potential gets added, and it will have some potential, some high potential. This charge Q possesses. And here at the bottom, I am making one more small arrangement. Okay, one small base is taken, and this is grounded. If it is grounded, its potential can be taken as 0. And here a heavy potential is there, very high value of potential is present. Is there potential difference or not? This is at high potential and this is at low potential. And this potential difference is extremely large. It is extremely large because potential of this charge Q is very large. Potential of this charge Q is very large because potential of this metallic sphere is very large. Potential of this metallic sphere is very large because high amount of charge, huge amount of charge got accumulated on this metallic sphere. I hope you understood. In Van de Graaff generator, ultimately our aim is to increase the potential of this metallic surface. There will be a limit. You cannot go to whatever value you wanted to go. Okay, depending upon physical dimensions and all, there will be certain limitations. Okay, till saturation you can go. What is saturation again? Saturation in the sense, for example, if a lot of amount of charge is present on this one, there could be a discharge. You can avoid that. You can enclose this entire apparatus in a glass chamber and you can evacuate that. Okay, but the thing is, you can go to saturated value of potential. Once we reach the saturation, what happens? Potential of this sphere becomes extremely large, and the potential of whatever charged particle you are going to keep inside this potential, to which you wanted to give acceleration, that charge's potential will be very high. If this charge's potential is very high, and if at the bottom where you have kept your target, this is the target, whatever small dot kind of arrangement I have made here, that is target. I want this particle Q to hit this target. Okay, so there is a potential difference. This is at high potential, this is at low potential. This potential difference will drive the charge, and when this charge is being driven, it will acquire some velocity or not. So if it is acquiring some velocity, it will have kinetic energy, and from where it is getting that kinetic energy, according to conservation principle, this energy, potential energy of this charge Q is converted into what? Kinetic energy. And further this equation, let me distinguish these two V's. I will take a velocity as small v. So from this equation, what you can write, V square is equal to 2VQ by M, or V is equal to under root 2VQ by M. And this is what our interest is. If you can manage to provide sufficiently large velocity to this charged particle, it can go and it can hit this target with high kinetic energy. If you have taken a single atom or some material is taken, and if you have taken a bunch of particles here, let us say alpha particles, all those particles can travel up to here and they can penetrate deep into the atom, and they can even bombard with the nucleus also. When these charged particles bombards with the nucleus, what happens? There will be fragmentation. It can break if energy is sufficiently large. Kinetic energy of this charged particle, if it is sufficiently large, what can happen? Nucleus can break, and that's what we are going to do. Okay, and further studies will be made. So this is how it works. This is how it works. And this particular theory is very important. So what is happening here? Whatever potential energy it is having, that is converted into kinetic energy. You can make sure that potential energy is very high by making sure that potential of this metallic sphere is very high. If potential energy is very high, according to conservation principle, the same amount of kinetic energy finally it builds up, isn't it? So that's, children, that is about working of Van de Graaff generator. Okay, thank you, students.